I'm Hadiju. Good morning, everyone. I'm Hadiju from UT Arlington. And today I'm here to present our paper, SoundLock, a novel user authentication scheme for VR devices using auditory-pupillary response. This is a collaborative work with Dr. Ming Xiao, Demoria Sherman, and my supervisor, Dr. Ming Li. Over the past few years, the virtual reality, or VR, has seen rapid development and a consistently growing popularity. And by 2030, the VR market is forecast to reach $87 billion. Nowadays, VR has permeated a variety of applications ranging from the entertainment to e-commerce, healthcare, education, and social media. At the same time, tremendous sensitive information is stored in and accessible through VR devices, such as personal media, bank info, and health status. If these devices are compromised, then adversarial access will cause data breaches and other critical consequences. Therefore, user authentication on VR is crucial for protecting users' security and privacy. Unfortunately, the user authentication on VR is still at the infant stage. Current solutions such as password, PIN, and pattern lock, they would require the handheld controllers for the credential entry, which is known for their poor usability. What's even worse, they are widely known for their vulnerability against bystanding observers. To mitigate these issues, researchers have developed biometric alternatives that utilizes the brainwave, the skull reflection, the eye movement, and the muscle reflection to authenticate legitimate users. However, these schemes require the specific sensors that are expensive and cannot be deployed to a wide range of off-the-shelf VR devices. Therefore, a convenient, robust, and deployable VR user authentication scheme on VR is in dire need. In this work, we explore the auditory-pupillary response, which is a reflexive mechanism involving multiple components of the human body. While receiving the auditory stimulus, which is like an audio track, our brain first passes this information to the neural pathways, which further control the iris muscles to increase or decrease the pupil size. And we see that the biological uniqueness in the neural pathways and in the complex structure of the iris muscles may show distinctive patterns for each individual. Based on this, our basic idea is to leverage this novel biometric for user authentication. To this end, we render an auditory stimulus in the VR device using the headphones, and at the same time, an eye tracker captures the real-time pupil size changes, which is like a biosignal used to verify the user identity. And it's worth mentioning that the eye tracker has been equipped through a variety of current commercial applications. Commercial VR devices, and it's also a future trend for the VR technology to include the eye tracking ability. To validate the feasibility of our idea, we conducted a measurement study where we invited 32 subjects, each listening to 20 different audio tracks as we collected their pupil size change data. And we randomly show some signals here on the left, and we further compute the Pearson correlation between each two signals and construct the confusion matrix on the right. As we can see, the pupil response show distinctive patterns when they're from different users, and within the same user, the pattern is more consistent. And we further show the signals of the same user but under different stimuli, and we see that these signals and the features are distinctive as well. So our first insight shows that auditory pupillary response can be an ideal biomarker for user authentication, and our second finding further addresses the cancelability concern, which is a common concern for most biometric systems. For example, say your fingerprint is stolen, it's stolen forever, and you cannot reset it because you cannot grow a new fingerprint. But in our case, even if your pupil response is divulged, you can simply update the corresponding stimulus to reset it. So we propose SoundLock, which utilizes the auditory-pupillary response for user authentication. The basic workflow can be summarized into the following steps. First, as the auditory stimulus is rendered, the pre-installed pupil lapse tracker will capture the pupil size data, which is a biosignal, and it's pre-processed to get rid of the noise and user blinks. And after that, we divide the clean signal into two phases, and we extract a set of morphological and statistical features from each phase. And since there's no prior work on this topic, we thoroughly investigate and propose a set of 60 features and further narrow them down to 20 that best reflect the user's biological uniqueness. After that, in the enrollment stage, a classification model is trained based on the user's enrollment samples. And during authentication, the pre-trained classifier is used to predict the user's legitimacy. Compared to existing work, SoundLock exhibits the following advantages. First, since all the user's biometrics are automatically gathered by the VR device, it does not require much of the user effort for credential entry. And second, SoundLock prevents the observer attacks since the user's eyes are completely blocked by the VR device. And third, SoundLock does not require any specific sensors and can be deployed to a wide range of commercial off-the-shelf VR devices. So far, we've only discussed the basic scheme where we only render one single stimulus. However, we observed that this would lead to limited entropy and authentication accuracy. So, inspired by the strong password selection criteria, we propose to render multiple stimuli to enhance the feature diversity. So an important question here is, how do we combine these multiple stimuli? A strawman approach would be to render all these stimuli to the user at their full length, and we concatenate all the user responses and use that as the credentials. However, this would introduce a very long authentication time in dozens of seconds, which impairs the usability. So to facilitate our discussion, we adopt KLD as the performance indicator. So KLD computes the divergence of a user's feature distributions P from that of a reference set Q. And a higher KLD would indicate a better expectable system performance. We observed that KLD is not uniformly distributed across the time of the signal. Instead, the features identified earlier tend to play a more important role in the KLD compared to the later features. So based on this observation, we propose to truncate the stimuli to preserve only the earlier features so as to save the authentication time at the cost of certain data loss. We also observed that the different stimuli will lead to different feature distributions. So we propose to choose only the stimuli that lead to the highest KLD when they are combined. So this motivates us to optimize the stimuli selection and their durations for the best performance time trade-off. All right, we formulate our optimization problem in this way. Our objective is to maximize the overall KLD while maintaining the entire authentication time within the practical threshold T0. And two variables here are M, which is a binary masking vector deciding whether to keep or discard each stimulus, and T, which is a vector indicating the time duration for each stimulus. However, directly solving this problem faces two major challenges. First, these two variables are correlated with each other and they cannot be updated simultaneously. Second, our objective function is nonlinear. This is because the feature distributions are non-differentiable. So to efficiently solve this problem, we propose a two-stage heuristic algorithm, where in the first stage, we aim to optimize M. So given a stimulus pool, we first try to identify the stimulus that gives the highest KLD, and we push it in the queue. Next, we search from the rest of the pool which stimulus gives the highest KLD when combined with the previous stimuli, and we push that in the queue. And we repeat this process until we get K stimuli that lead to the highest KLD when they're combined. And these are our selected stimuli. And in the second stage, we use the approximate gradient descent algorithm to further optimize the time duration for each of the stimuli. And this is our algorithm. For more details, please refer to our paper. We built our prototype on an HTC Vive Pro with a pre-installed pupil labs eye tracker, and the headset is physically connected to a local server, and the software is implemented in Unity. We recruited 44 participants from UT Arlington and asked them to perform a series of tasks, such as enrollment, authentication, attack simulation, consistency test, and user study. We first show the overall performance of SoundLock and compare it to the existing works. And we can see among them, SoundLock achieves the lowest error rate and the highest F1 score. And it's worth mentioning that SoundLock only requires 5 enrollment samples. Next, we derive the entropy of SoundLock using our collected dataset, and we compare it to existing works. And among them, SoundLock ranks the second highest in the entropy, only lower to iris, but iris recognition cannot be implemented in commercial VR devices. Then we show the error rate as a function of authentication time and the number of stimuli. And we can see the error tends to decrease with a longer time and with more stimuli with a marginal benefit. And we can derive the optimal trade-off at 7 seconds with 2 stimuli. We further evaluate the SoundLock under various real-world scenarios and study their impact. And compared to the other user motions, the eye movement incurs the highest FRR. So we would recommend users to keep their eyes still while doing authentication. But on the other hand, the FAR remains stable, which means user motions does not impact the system security. We also show the impact of ambient noise, and as expected, a louder noise would have a higher impact. And we also noticed that the white noise would affect the error rate the most. But we also see the performance is consistent under more real-world settings, such as office and home environments. Our user study consists of a pre-study and post-study before and after the experiments. And in both studies, users are asked to evaluate their perception of SoundLock based on by responding to the same questionnaire of 9 questions. And overall, SoundLock is well perceived by users in both studies, and we also notice an improvement in the post-study, which means that SoundLock has exceeded their expectations. Finally, users are asked to answer to 3 open questions regarding their overall experience, their concerns, and their suggestions, and they have provided valuable feedback that guided our future work. For example, several of them questioned the robustness against consanguinity, which is a reasonable question, and we do not have a clear answer yet due to the limited data, but we plan to investigate this in the future. Another participant suggested extending our idea to smartphones using the speaker and the camera on the phone, which points out another direction of our future research. For more detailed analysis and discussions, please refer to our paper. In conclusion, we propose SoundLock, which utilizes the auditory-pupillary response for user authentication. We identified an optimization problem and proposed a 2-stage heuristic algorithm to efficiently solve the problem. And we conducted extensive experiments which show that SoundLock outperforms state-of-the-art and is well perceived by the users. For more details, please refer to our paper. Thank you.
I really thought in external room UCI. So I'm wondering if you consider any changes in behavior over time, because by people associated with the stimulus is very behavioral oriented thing, and
Yeah, and that's a very good question. Actually, we consider this in our paper due to the technical condition and presentation. So, we identified the so-called template aging problem, which means the user's biometric will change over time, and we used the commonly adopted and adaptive strategy to account for that. Which is proven very useful in our evaluation. You can please check our paper.
Thank you very much. Other questions?
University expert. Thank you, Hadi. My question was about the threat model. So the defense that you propose here, what would a typical attack look like? What type of attacks are you preventing here?
Okay, so you're asking what types of attacks are used here. Okay. So in our experiment, we mainly focused on one type of attack, which is the impersonation attack. And in our paper, we also analyzed why the other attacks are not going to work efficiently. So we do not have to consider other types of attacks.
What does impersonation techniques?
The impersonation attack is pretty simple and straightforward. It's just the attacker mimics the legitimate user's input. They also do not need to do anything specifically. They just wear the headset and then listen to the same stimuli, and their pupil size is used to mimic their legitimate users' biometrics. So this is the type of attack we consider.
Thank you. But this makes me concerned about privacy. Maybe they play the marker at my pupils, reveal that I'm excited about it, something like that. So, you consider this kind of this. I suppose your pupil been dilated can reveal something about whether I'd be excited about something.
Yeah, that's also a great question. And one user that or is sharing our study, and we believe this is current research cannot accurately relate people's eyes to your detailed like the behavior of their brains, motion activity, but if they show effect on the actual emotion, that is possible, and we can consider to future work. So far, we only use this strategy as in the lack of the Touch ID and Face ID. So we capture the biometric symbols are smart application and it's protected by the integration methods. So this will be public, but we will use it in the future.
Cool. Another idea for NDSS 2024.